Hi guys, so today we're here to present on how seawater and wastewater can help in the production of green hydrogen. So imagine a future powered by clean energy where our cars, factories and cities run on a fuel that produces nothing but water vapor. That fuel is green hydrogen, a symbol of hope for a carbon-free world. Green hydrogen is made by splitting water into hydrogen and oxygen using renewable electricity, a process called electrolysis. It's completely clean and renewable, but there's a catch. To produce just 1 kilogram of hydrogen, we need at least 9 liters of pure water. Multiply that by the millions of tons the world plans to produce, and suddenly this green fuel starts looking a little less green. Because the truth is, fresh water is running out. Only a tiny fraction of the Earth's water is drinkable, and we already need it for farming, drinking, and for life itself. If we start using huge amounts of it to make hydrogen, we risk creating a new kind of resource crisis, one not of energy but of water. So the question becomes, can we make hydrogen without competing with life's most essential resource? There's where the idea of going beyond fresh water begins.
When we think of abundance, we think of the ocean, as it covers 97% of the water in our planet. If we could somehow turn seawater into hydrogen, we'd have nearly unlimited fuel. However, this is harder to do in practice. Seawater is full of salts and minerals such as sodium, chloride, magnesium, potassium that can corrode equipment. There are two main paths scientists are exploring for seawater electrolysis, which are direct and indirect seawater electrolysis. In direct electrolysis, we feed seawater straight into the electrolyzer. It's simple, but it's dangerous. The chloride ions cause unwanted side reactions, creating chlorine gas and corroding the equipment. Also, as the reaction continues, the pH rises, forming calcium carbonate and magnesium hydroxide that block active catalyst sites, lowering overall efficiency. The indirect method, on the other hand, first treats the seawater, removing salts and impurities before electrolysis. It's safer and more efficient, but it needs extra energy and infrastructure, making it more expensive. Different electrolyzers like alkaline, anion exchange and proton exchange membrane systems are being tested to find the best balance. Seawater is abundant, but its chemistry needs to be carefully managed.
Where seawater offers abundance, wastewater offers opportunity. Every day, billions of liters of wastewater flow from our homes, industries and cities, packed with organic matter, nutrients and trace metals. It's usually treated as waste, but it's actually a valuable resource waiting to be tapped. Because wastewater contains suspended solids, salts and complex organic compounds, pre-treatment is often needed to protect the electrodes and maintain efficiency. But this extra step can also recover valuable materials like phosphorus and nitrogen, adding to the sustainability of the process. This isn't science fiction. Pilot plants in places like Japan, the Netherlands and California are already integrating hydrogen production into municipal wastewater treatment systems. Researchers are also developing microbial electrolysis cells where bacteria break down organic matter and release hydrogen, using biology to assist electrochemistry. It's still an emerging technology, but it holds enormous promise, a system that cleans our water, recovers resources and produces clean energy.
Using seawater and wastewater can present technical and environmental challenges. Seawater must be desalinated while wastewater needs treatment to remove organics. There are also environmental issues regarding desalination that creates a brine as high salinity waste that must be carefully disposed. Economically, these processes are usually expensive, mainly because of the extra treatment steps and the need for advanced materials. And looking ahead, research is focusing on low-energy desalination methods and also exploring microbial electrolysis. In conclusion, seawater and wastewater are promising alternatives for green hydrogen production that can promote a circular economy.